All right, so we'll go ahead and start lecture 3. So I'm gonna do chapter 7 and 8 as video lectures, and then chapter 9 we'll do in class. So chapter 7 is all about solutions. So to get ourselves familiar, there's a lot of terminology with solutions. So solution is a homogeneous mixture, special emphasis on homogeneous, with two or more substance that in which the components are present as atoms, molecules, or ions. The solvent is the most abundant substance. And usually this is water, but it doesn't have to be. It's also usually a liquid, but again, it doesn't always have to be. The solute is what you're dissolving. Immiscible is a term for saying that the solute doesn't dissolve. It's the same as saying insoluble. Miscible means that something does dissolve. And again, it's the same thing as saying soluble. Saturated is a term for when the solution has the maximum amount of solute that it can have. So when we put solute into water, right? If I was to, let's say our solute was just table salt and that our solvent was water, at some point, I can add so much table salt that it won't be able to dissolve. Basically, we've maxed out the amount of table salt to water ratio. So the point at which you are at right before the table salt stops dissolving, the excess stops dissolving, is called saturated. So it's when the solution has the max amount of solute it can have. Supersaturated is when the solute is greater than the saturation point, and therefore some solute will dissolve and precipitate. So I actually am not going to lie to you. I did not know what this word meant until about a year ago, supersaturated. And I didn't know that it meant that the solute would precipitate out. I just thought it meant, oh, it's got a lot of solute. It's super saturated, it's super concentrated. So I was trying to repeat an experiment that a PhD student who was no longer in the lab did. And so I was trying to repeat her experiment. I kept reading her lab notebook over and over, and I was like, I'm doing this all perfectly. Why won't the stuff dissolve? And I honestly can't remember what the solution was. But I remember I was heating it up, and then all of a sudden, once it came back to room temperature, it would just crash out of solution. It would just precipitate out. And I just couldn't figure it out. And finally, I started talking to some of my coworkers in the lab, and they're like, oh, it says in her lab notebook that it's a super saturated solution. And I was like, yeah. They're like, so it's going to precipitate. I was like, oh, I thought that was a bad thing. Okay, okay. So that's my story about supersaturated. If something's dilute, it's well below the saturation point. So I'm sure we're familiar with that term. Aqueous, I brought up this term in the last lecture, but aqueous, sometimes denoted as AQ in chemical reactions or equations, is when a solution, so basically something is in an aqueous solution after it was a solid, went into liquid, and then now it's in solution. So when we're writing those chemical equations, AQ means that it was a solid and then it became dissolved. So this is your OWL question 1, is just talking about using this terminology. So in this drop-down menu, it's just asking you what state of matter it's going to be. So solid, liquid, gas. So my particular question says that a homogeneous mixture is made by dissolving 9.11 grams of potassium nitrate in 1,000 grams of water. This is an example of a liquid solution. If the mixture, in the mixture, potassium nitrate would be the solute because it's what's dissolving. And then water is the solvent because it's what's in excess and it's what's doing the dissolving. So solubility is basically determining, can it dissolve? So previously we talked about ionic compounds and covalent compounds. And ionic compounds were these solutions that ended up were these compounds that ended up creating basically really strong attractions between ions. They transferred electrons and then they became these really strong positive and negatives. And so in water in particular, ionic solutions are really soluble because water, as we know, is polar and has these dipoles where it has regions of negative and positive. And basically this water can go in there and separate these positive from the negative with their own positive and negative. It goes in there and basically breaks apart the ions. Covalent compounds are a little bit more tricky. And again, this example is in water. So in this covalent compound, we have a polar molecule, and we know it's polar because, again, it has these ends of positive and negative. It has these dipoles. And polar molecules, because they, again, kind of look and act like ionic, they have those positive and negative dipoles. Water can get in there and pull these molecules apart by attracting their water's own positive and negative ends to the compounds, positive and negative ends. So like I said, typically ionic solutions are soluble in water, but there are a few exceptions. And to know that, we use this chart. So I showed you another version of this chart previously in our last lecture. This is just another version of the exact same chart. But basically, to know if an ionic solution is soluble in water, we have to look at this chart. There's no special rules or anything. And so it just works as if, if I had this solution, let's say silver iodide, I would look for silver somewhere in this row, iodide. So I'd find where they cross. And silver iodide is actually one of those exceptions. It's insoluble in water. But like I said, most ionic solutions are, and you can tell that, right? Because most of this chart is this light blue color. So we only know ionic solutions based off this table. Covalent molecules, though, are a little bit trickier. And so we talked about, I showed you that example just a minute ago with the polar molecule, right? Because they have dipoles. So polar, because they have dipoles, these plus and minus ends. they are actually soluble in water, right? Because the plus and minus ends of oxygen can kind of compete for the plus or minus ends of the polar molecule. But nonpolar, right, in which it has those no dipole, right, it's neutral throughout, is not soluble in water because there's no way for the water to kind of pull it apart from its partners. So solubility for covalent compounds is a little trickier, but there's this general rule called like dissolves like. And basically, polar molecules will dissolve in polar solutions. Like dissolves like. And nonpolar molecules will dissolve in nonpolar solutions. So an example, CH4 is nonpolar and is not going to agree with water. But carbon dioxide is also not polar. But ammonium, NH3, is polar and it will dissolve in water. So looking at your OWL question 2, it asks you if liquid acetic acid and water, and again, your example might be different, but the process in which we go to solve this is going to be the same. If acetic acid and water will dissolve, if they're going to be soluble or insoluble. And so first you want to determine, I hope this is all water for you guys. I hope. I don't know. I can't see the whole bank of questions, but you want to determine which each molecule, if it's polar or non-polar. And so we know that water is polar. Acetic acid, I have no clue, but I did look up the structure and it looks like this. And so this is a little complicated, but basically it does have dipoles here and here, and they don't end up canceling it out. It's actually very polar. If you're having trouble figuring out if your compound is polar or not, just Google, is acetic acid polar? And so they are both polar. And like dissolves like, we want them to be the same. And so this solution will be soluble. This drop-down menu, for me, it used the terms miscible and immiscible, which, like I said on the first slide, are the exact same as saying soluble and insoluble. So we can make the rate in which something solubilizes faster, but we can never really change it. So if that ionic chart says that something is not soluble, doing one of these 3 things is not going to make it soluble. But there are solutions that are soluble, but that are really tough, if you will. And so one of these solutions is EDTA. I honestly don't remember what EDTA stands for, but EDTA is basically this molecule that binds really well to heavy metals. And so I use this in the lab. I have to make stock solutions of this. And at 500 millimolar, right? Millimolar, we learned our prefixes. So this isn't even that concentrated, but this is its saturation point, roughly. This sucker, it will dissolve, but it will take me so long to dissolve. I will put it on a stir plate and I will stir it, and I could stir it for like 2 hours before I see it dissolve all the way. Sometimes I heat it up to make it go a little faster, but once I have it dissolved, it's dissolved. It doesn't come out of solution. And so we can do things to increase that solubility rate, like I just talked about, putting it on a stir plate, stirring it up, crushing up those ions, heating it, right? So you can't, like I said, you can't change if something's soluble or not, but you can try to increase the rates. This solution, 5 molar NaOH, is very soluble. In fact, when I usually put, I set out my beaker of water and then I measure out my NaOH. When I pour my NaOH into it, it almost immediately turns into the solution. And it's so fast that it actually gives off heat. At 5 millimolar, sometimes the beaker will be hot because this reaction happens really fast. So if I wanted to slow that reaction down for whatever reason, I could put it maybe in the fridge, but NaOH is very soluble and it just loves water. It loves to be in water. So I talked about this previously, but I wanted to point out that the states of matter are usually listed in chemical equations, where G is for gas or a gaseous state of matter. AQ is for aqueous, which means it's been dissolved in solution. S is for solid. And L, I don't have an example of L here, but L is liquid. And so in this example, they put two aqueous solutions together and they ended up doing a double replacement in which the new ionic compound precipitated out. It became a solid in the solution, while remaining sodium nitrate hung out in the solution. So it just goes to show that not all ionic solutions are soluble, but we can only determine that based off that chart. So concentration is probably a term we're somewhat familiar with. So this is basically putting a physical number on the amount of solute and solvent. So basically, you're able to quantify how concentrated a solution is, or not concentrated by that matter. So some common units are molarity, percent, weight. So it's commonly abbreviated WW, but this stands for weight. Percent, weight, volume, commonly abbreviated WV. Percent volume, commonly abbreviated VV. And so basically, these are all different ways of measuring concentration. So weight is not a very common one. I'll tell you the most common two here are molarity and weight volume. But percent weight is where I would weigh my solute. So let's say I have 11 grams of table salt, sodium chloride, and then I put it into water. So percent weight, I weigh my table salt and I'd weigh my water. So let's just say it weighs like 100 grams. And so then I would divide the amount of solute that I put into solvent and times this by 100 to get myself a percent. We'll do some practice. I'm just trying to show you an example. So basically you have 11% weight here. And you would do the same for weight volume. Maybe I still have 11 grams, but this time I measured my water and it was 1,000 milliliters, let's say. So I do the math again. I'll show you here in a second. So molarity has an abbreviated unit as big M, where big M is the moles over liters. So basically, whenever something is in molarity or big M, you're quantifying the number of moles over the number of liters. Percent volume, which I just kind of gave you a little intro to, is the weight of a part over the weight of the total times 100. And that's going to equal our weight. And so usually this weight of the part is your solute and the weight of the total is your solvent. But basically it's small part divided by big part times 100. And so the same goes for weight volume. So we have weight of the part over volume of the total times 100. And that's going to get us our percent weight volume. So most of the, when it's the same, if it's weight or volume, doesn't matter if you weigh your substance in grams, milligrams, kilograms, as long as you have the same on top, same unit on top as bottom. And that's true for the volume, same unit on top and bottom. But the weight volume is the outlier. And we want the weight of our part to be in grams. So grams on top. And it likes the volume to be in milliliters. So milliliters on bottom. And then, times 100. So basically I just rewrote this formula. And so to finish it off, volume is the volume of the part over the volume of the total times 100. It's going to give us our percent VB. Okay, so that seems like a whole lot of mumbo jumbo probably right now. Let's do some practice and hopefully it'll start to make a little bit of sense. So here's a molarity practice problem, or big M. So just a reminder, big M is moles over liters. So seawater contains roughly 28 grams of sodium chloride per liter. What is the molarity of sodium chloride in seawater? So I have grams and I know I have 1 liter. So I have my bottom part. I don't know how many moles, but I do know I have 1 liter. We know how to go to grams to moles. We're going to use, to get to grams to moles, we use the molar mass of the compound. And so specifically for NaCl, it's 58.44 grams per mole. So we'll have to do some math before we can plug in this number. So I'll start with my given quantity, 28.0 grams of NaCl. I want to get out of grams of NaCl and into moles of NaCl. I know that 1 mole equals 58.44 grams. And that's going to get me 0.4971 moles of NaCl. So now I have my number of moles, I have my number of liters, and now I'm ready to divide moles by liters. So let me go ahead and now move. I can fill in this now with this number. Now it's just a matter of dividing, all right? Well, fortunately our bottom number is just 1. So this comes out to 0.4791 molar. So let's do now a practice problem. So again, this is calculating molarity. This question is asking, what is the molarity of chromium iodide of the resulting solution? So just a reminder, molarity is big M, which is moles over liters. So a student weighs out 11.8 grams of chromium iodide and transfers it to a 300 milliliter volumetric flask and adds enough water to dissolve it. It says they then add the water. It's repetitive. Basically, we have part of we know we want liters over moles. We're given grams here, but we know how to take this grams to moles. We're given milliliters here, so we're going to need to take that from milliliters to liters before we can plug this in. So I'm going to start with going from milliliters to liters. I don't know, just sounds fun. Okay, so 300 milliliters. I want to divide by milliliters and get myself into liters. Which is bigger? 1 liter. And I know that there's 1,000 milliliters in 1 liter. So 300 divided by 1,000 is 0.3 liters. So now I have my bottom number. Now I want to go from grams to moles. So you're going to have to look up the molar mass of chromium iodide. I will tell you what it is. I mean, you might have to look it up for your own if your compound is different, but for chromium iodide, it's 305.8 grams per mole. So I'll start with my given quantity, 11.8 grams. I want to get out of grams and into moles. There's 305.8 grams and 1 mole of CrI2. So I'm running out of room here, so I'm going to put the answer down here. The answer is 0.038, and I'm going to carry a bunch of digits here. 587 moles of chromium iodide. So now I have my top number. Don't worry too much about rounding off to your sig figs just yet. Carry as many digits as you want. When you go to do this final calculation here, the big M calculation, that's when you worry about your sig figs. And so for this, moving forward, I think I said this previously, moving forward, always kind of forget about the sig fig rule to some extent. Remember it for the exam, but just use the number of sig figs in your given quantity. So here, both of my given quantities have 3 sig figs. This one has 3 because they put a decimal after it. They made it these 2 zeros significant. And so I want my answer to have 3 sig figs. So my calculator gives me something like 0.29 something something. I'm just going to leave it at 0.29 because that's 3 sig figs. This is big M of chromium iodide. So I would go ahead and fill in that answer. All right. So we have another molarity practice problem. This time they have given us big M, and they have given us grams, and they want us to solve for volume in milliliters. So we got quite a few steps here. First, I want to go from grams to moles. Next, I'm going to use big M as a conversion factor to get the number of liters, but they want liters, or they want the answer in milliliters, so then I'll go from milliliters to liters. So my given quantity here is grams. So starting with 1, going from grams to moles, I'm going to start with 4.80 grams. This crazy compound has a molar mass of 158.17 grams. Now, your compound might be different. You would have to, they give you a name if you just want to Google molar mass of whatever it is. So once I do the math, I divide 4.87 by 158.17. I get 0.03078 moles. So I went from grams to moles. So again, this question is giving us big M, which we know is the ratio of moles to liters. It's also giving us the number of grams, which we've now converted to moles. And it wants to know if we have this concentration and this amount and this volume, in this moles, what is the volume? So now that we have gotten ourselves into moles, we can now use that big M as a conversion factor. So I'm going to start with the number we just calculated as my given quantity. So how do I know what goes where? So we know that big M is moles over liters. In order to use this as a conversion factor, I can flip this and say mole over liter, but I want this number to be married to the mole. So if I'm going to flip it, I can't leave that 0.179 on top. I need it to stay with the mole. So once I divide this, I get 0.017 or 0.172 liters. So I'm almost there. I then need to take 0.172 liters, and I want to make it into milliliters just because that's the answer they're looking for. So I want to cancel liters and get into milliliters, which is bigger. 1 liter is bigger. 1,000 milliliters go in a liter. And this is going to give me 172 milliliters. So I'm going to round to 3 sig figs, just because they use 3 sig figs in both of the given quantities. So I want to show you an alternative way of doing this as well. So I'm going to clear this and show you a different way of solving this. So another way of solving this that if you found that difficult, this might be a little bit easier, is setting this 0.179 equal to moles over liters. We want to solve for this. So I'm going to label that as X. We have this quantity, we just need to put it into grams. And I deleted that from our last, I erased the whole slide there, but we did just already change this quantity to grams. I'm sorry, to moles. And it was 0.0307. So another way of doing this is just to plug that in here and then solve for X. This is probably a little bit easier thinking wise, but you have to be careful with problems like this with X on the bottom. So if we multiply by X on both sides, that gets rid of our X on this side, but we now have X on this side. To get X by itself, divide by this. And so once we plug this into our calculator, it's going to give us that 0.172 liters. And again, we just have to take one extra step in changing this to milliliters, which we did previously, just because that's what the question asked for. Okay, so you're probably sick of big M, of molarity. So let's do a practice problem with percent weight. And so percent weight, this is like your question 4. So sometimes you can't just figure out that it's percent weight. It needs to tell you just the same way it needed to tell you they wanted you to solve for big M. And so here the problem reads, if I have 21.2 grams of an aqueous solution of chromium iodide that contains 3.39 grams of chromium iodide, what is the weight percent in the solution? So it might be a little confusing because they both say they're chromium iodide, and what the heck am I supposed to do with that? But if we remember, part over total times 100. So 3.39 is smaller than 21.2, so I'm going to put him on top. When we do percent weight, doesn't matter what the unit is as long as it's the same on top and bottom, and both of them are grams, so I'm happy. So I need to times it by 100 to get a percent. So it's just a matter of dividing 3.39 by 21.29 or 21.2 timesing by 100. And I get 15.990%. I want to take this to 3 sig figs because that's the same amount of numbers, same amount of sig figs as the numbers they've given me. So I'm going to round this to 16.0%. So your OWL question 5 is similar, but this time it's asking for percent volume. So an aqueous solution of calcium acetate is made by dissolving 5.66 grams into 100 milliliters of water, blah, blah, blah. What is the weight volume percentage? So again, this is part over total times 100. Weight volume is tricky though. They want you to have it to make sure it's grams over milliliters. They're finicky about their units, but we are given our part in grams and our total in milliliters. So we don't have to convert anything. It's a matter of just dividing 5.66 grams over 100 milliliters and multiplying that by 100. And so when I put that into my calculator and round to 3 sig figs, I get 9.90%. So lastly, in the concentration category, we have our OWL question 6, which is asking for percent volume. So part over total times 100. Percent volume doesn't care about the units as long as they're the same on top and bottom. And so 29.7 is my part because it is smaller than 300, which is my total. So 29.7 milliliters over 300 milliliters times 100. So they're both in milliliters, so we can go ahead and plug it into our calculator. Oh, I'm sorry. On the last problem, I said 9.9. When you do the math, the last problem is 5.66%. This one is 9.9%. My apologies. Okay, so moving on to the dilution equation. So basically the dilution equation is how we measure the change in concentration, how the concentration changes. So say C1 is the initial and C2 is the final, how it changes when we dilute the solution. And so somebody out there developed this formula, C1 times V1 equals C2 times V2, where C is the concentration and V is volume. This formula kind of reminds me of the combined gas law formula. It's very similar looking and works very similarly as well. So you want to make sure that you keep C1 and V1 on the same side. And you could almost even think about the one as being the initial. C2 and V2, same thing. You want to keep them on the same side of the equal sign. And you can think about them as being the final. So let's go ahead and look at a practice problem. So it says we're going to dilute 175 milliliters of 1.6 milliliter solution of lithium chloride to determine the new concentration. So let's think about this. I have a beaker. This is my initial, or my 1. I have 175 mils of 1.5 molar solution. I'm going to add to that beaker to bring it to a final volume of 1 liter, but I don't know the new concentration. So let me write the formula here just as a reminder. So let's go ahead and define our values. C1, concentration of the initial, is 1.6 molar. V1 is 175 milliliters. C2, we're solving for. We don't know. V2, we know is 1 liter. So there's one trick with using this equation, is the units. It doesn't matter which units we use for concentration or volume, as long as we use the same units on each side. So if my C1s are in molar, I want them both to be in molar. And since we are solving for C2, we know that it's going to come out in molar. I want my volumes to be in the same unit, and right now they happen to not be. So it doesn't matter if I change the 175 to liters and make them both liters. It doesn't matter if I change the 1 liter to milliliters and make them both milliliters, as long as they're the same unit. And so I'm going to go ahead and make V2 1,000 milliliters, just because for me the math is easier, but it doesn't matter. So now it's a matter of plugging that into this equation. So I have 1.6 m, goes where my C1 is, 175 milliliters, my V1 equals C2 we're solving for, so I'm going to go ahead and put X times V2, which we've changed to 1,000 milliliters because we want to keep those units consistent. I'm going to divide by 1,000 on each side to get X by itself. And after I plug this into my calculator, X equals 0.280 molar. I probably only want to take that to 1 sig fig. 0.28 molar, just because we want to use the least amount of sig figs that's given in the given quantities, and that just happens to be 2. All right, let's do another one that's a little bit trickier. So this is like your OWL question 8. I specifically, not all of your OWL question 8s are going to be this trickier version, but I specifically chose this one because it doesn't give us necessarily the total volume, and we have to solve for the total volume. So let me read the problem. In the laboratory, a student adds 51.7 milliliters of water to 10.2 milliliters of 0.606 milliliter or molar of hydrobromic acid solution. What is the concentration of the diluted solution? Assume the volumes are additive. So let's draw our pictures again. So my initial beaker, my 1, I have 10.2 milliliters, 6.06 molar. Sometimes reading the problem, it's a little tricky to figure out which volume goes with which concentration, you know, which ones to keep on the same side. And my recommendation is if their numbers are separated by an of or some similar thing, if that means that they're married to each other and that they're going to be on the same side. So they're either both 1 or both 2. In this case, we're going to call them 1 because they're our initial. It then says that we are going to dilute this solution by adding 51.7 milliliters. And we want to solve for the concentration. So this one's a little tricky because in the last problem, it was telling us our total volume of our 2 was 1 liter. Here it's saying I'm adding 51.7 milliliters. So basically it's saying you got to do the math and add these 2 volumes together. So let's go ahead and do that. They're both in milliliters, so we can go ahead and add them together. We don't need to do any kind of unit conversions. So 51.7 plus 10.2 is 61.9 milliliters. So my V2 is now 61.9. My V1 is the 10.2. My C1 was given to me 0.606 molar, and we're solving for our C2. I don't know. So just a reminder, the equation is C1 times V1 equals C2 times V2. So it's a matter of setting up this equation. So our C1, 6 molar. Oh wait, well, let's double check that our units are correct, right? So our V1s are both in milliliters. That's great. Our C1 is in molar. We don't know what our C2 is, but we know that it's going to spit it out to us in molar because the units have to be the same. Okay, so going back, so this was our C1, our V1, 10.2 milliliters equals C2, which we're solving for, so I'm going to put X, and then V2, which we had to use that additive property there to get 61.9. So when we divide both sides by 61.9, we get X by itself. And when I go ahead and plug this into my calculator, I get X equals some crazy number, 0.09985 molar. I'm going to go ahead and round that to 3 sig figs, just because that's the amount that's given in my problem. So leading zeros never count. I'm going to go ahead and round this to 999 because this 5 makes this jump to a 9. Okay, so that's the dilution equation. So bringing this all back to stoichiometry. So we can use stoichiometry with concentration as well. So I forgot to put up the map here, but we can use concentration in stoichiometry, and I'm just going to abbreviate stoich. I think I might have spelled that wrong on the slide. I never know how to say stoichiometry or pronounce it. Is it stoichiometry? I don't know. Who knows? So I don't believe you have an out problem like this. But I just want to introduce the idea. I also don't think that you have a question like this on your exam, but I think it's kind of silly that they didn't put this on your exam, because this solution stoichiometry, I believe, like, to me, would be something you potentially could use in nursing. So I just want to introduce the idea. If you're curious, if you want to go ahead and skip ahead because you're like, Kayla, why are you telling us something that we don't need to know? Okay, fair enough. So what volume of a 0.2 molar NaOH solution is needed to exactly react with 0.15 moles of HCl? So where do we start? We have two given quantities. So when you have two given quantities, you want to start with the one that can't be broken down and used as a conversion factor. So big M, we know, is moles over liters, all right? So we can break this down into moles over liters and use it as a conversion factor, where moles, that unit is just straight up moles. And so I'm going to start with the unit that's just point blank moles. So we're in moles of HCl, and it wants to know how we get to a volume of NaOH. So let's go ahead and get into moles of NaOH. So to get out of moles of HCl and into moles of NaOH, we want to use the mole to mole ratio. We want to use those coefficients. This problem is balanced, and all the coefficients happen to be 1. So when I do the math, I get 0.15 moles of NaOH. I am now in moles of NaOH, and I want to know what the volume is, and I'm given molarity. So we know that molarity is moles over liters. So I'm going to set this up as the molarity that I'm given equals moles over liters. And we have now solved for moles, and the question asks us for a volume, so it makes sense that our liters are what we need to put in to solve for as our variable, as our x. So I'll multiply x by both sides to get x by itself. I also need to divide by 0.2 by both sides to get x by itself. So now when I plug this into my calculator, x equals 0.750 liters. So that was just a little crash course, little quickie to solution stoichiometry. I understand if it was a little overwhelming. I will preface that I don't believe this is on the exam. I'd have to double check my modified study guide I made, but you didn't have any AL questions. I know that. So, but if you're curious, because I know I do think this is something using molarity to concentrate or to calculate a volume is definitely relevant to nursing. So electrolytes, what are they? Right? We've heard the term electrolytes. We think about it in like sports drinks. We gotta replenish the electrolytes. But what are electrolytes? So by definition, electrolytes are solutions that can conduct electricity. So basically, it's full of ions in solution, right? So you can think of NaCl in solution, right? It's got a bunch of ions floating around. They've been disassociated by water. They have technically the ability to conduct electricity. Our body has the ability to conduct electricity. Not very well, but you know. So there can be strong electrolytes and weak electrolytes. And strong is based off of how the solutions in the ions disassociate. So a strong electrolyte is going to disassociate very well, meaning it's going to be very soluble. It's going to dissolve very easily. I think dissolve has two S's. Oh, dissolve easily. Whereas weak electrolytes still have the ability to still have ions in solution, still have the ability to conduct electricity, but they're not very soluble. They poorly dissolve. Where non-electrolytes, just point blank, cannot conduct electricity. There's no ions in solution. So something just point blank did not dissolve in solution. So now moving on to diffusion. What the heck is diffusion? So diffusion is the ability of a solute to move from high concentration to low concentration. And so we see this a lot in everyday, right? Here, this little picture, you put some food dye in some water. It's highly concentrated here. Once it hits the water, it starts to diffuse, starts to get evenly and make a homogeneous mixture. When I was in, very early high school, freshman or sophomore year, I took a class. It happened to be a biology class, but we were talking about diffusion. And my teacher she had the best analogy for us. And I still think about it to this day when I think about diffusion. She brought in a can of like air freshener, or Lysol, or some kind of air freshener thing. And she stood at the corner of the room and she sprayed it. And she told us to raise our hand when we smelt it. And so she raised her hands immediately, right? Because she smells it right away. She's right there. And then slowly, the kids that are a few feet from her raise their hand. And then eventually, the people in the back raise their hand. It takes a minute, but they eventually all raise their hand. We all have our hands raised. We can smell this. That's diffusion. Moving from a high concentration to a low concentration until you have this even mixture and stuff is diffused all around the room. And so we can apply this to osmosis, which is specifically the diffusion of water, right? So it's the same principle, moving from a high concentration to a low concentration in order to make even homogeneous mixtures, right? It's just the movement of water through diffusion. It's another way of thinking about it. So you don't need to necessarily know this for this course, maybe in a biology course or anatomy course, but osmosis is usually used to when talking about blood cells, how our blood cells diffuse water in and out. And so I just wanted to put that, the blood cell example. It's not that you need to know those as vocab words. You mostly just need to know what osmosis, the definition of osmosis is. But if you wanted to take it a step further, or if you've already had a biology class and covered this, there you go. And so our last little vocab is dialysis. And at first you're like, for me, when I think of dialysis, I think immediately of the kidney dialysis when people have failing kidneys and they go to dialysis. That's kind of slang for what's actually happening here. But dialysis is, again, a deeper form of diffusion. Even you can even think about it as a form of osmosis. So there's diffusion. Osmosis is a type of diffusion. And dialysis is a type of osmosis, if you want to get technical. But dialysis is movement of water across a permeable membrane. So permeable, what the heck does that mean? It means that the membrane will allow some things to pass through, but not all. It's got little tiny pores, and those pores are basically allow things in and out based off of size. So right now, we see this little sack of ions and fluids, and it says it has colloid particles and small molecules, ions. And so right now, this is all at a high concentration inside this membrane. When we put this into a water solution, the ions, oops, I'm sorry, that's not the right word. And I'm going to use red just to make it more visible. They're in a high solution, so whatever can diffuse out wants to diffuse out. So the ions diffuse out, the small molecules diffuse out. But these colloid particles, they are large and they can't cross the membrane. They're going to stay in the membrane. And colloid just means that they're larger particles. It's not any specific thing. So we can apply this to kidney dialysis, right? So I found this graphic. It's a little more detailed than I would like, but it's a nice graphic. So basically, when you have to undergo kidney dialysis, it's because your kidneys, who do the same job as this dialysizing membrane, can't filter, can't move from high to low. They've lost that function. And kidneys filter our blood, right? So in kidney dialysis, we use a machine to filter the blood for us. And so the blood is removed, right? It goes through this permeable membrane, right? Just like this membrane, where we can filter out the bad stuff, right? We can get out all those ions and stuff, the stuff basically you pee out. Keep all the good stuff we want. Maybe we don't want our cells to float out. Maybe we have some good important cells hanging out in our kidneys, some good stuff. Keep that in. So we filter that out using a membrane, a permeable membrane, and concentration gradient going from high to low. That's a concentration gradient. Now we have good clean blood that we kept the important stuff in, like cells, and we can return it to the body. So we filter out the bad stuff. Well, it's not necessarily that it was bad, but The ions and stuff were important at some point, but we filter out what we don't need. I should word it like that. We no longer need. All right, so what do I need to know from this slide? That colloids can't cross the membrane. And that concentration gradient, it likes to go from high to low. All right, that is the chapter, or the end to chapter 7.